Good morning, folks. How are you today? Last Friday, we had the test number one. It went very smoothly. I want to tell you about the test one and overall statistics. There was one person who scored the maximum 100%, one person who scored minimum 65%, and the mean and median were both 78%. Usually on my test, they are more like 81%, 82%. And it might be just that this time many of you may have missed one more question than in the past. But any case, let's look at total so far. What does the total include? Includes the first 9 quizzes, the first 5 labs, and this test one. So this is all the material that you did before test one. So again, one person scoring 100%, it's actually rounded up. Minimum score 63. And here is the key part. Mean and median are both 84%. That is usually the case in most of my courses. Mean and median are really around 82 to 84%. So you are doing very, very well. Please continue to do so. I believe these slightly lower scores are from the students who I believe missed a few quizzes. So please do not miss any quiz. Please keep up the good work. Okay. Next topic. We just finished Taylor series in one variable. And I said basically Taylor series allows us to predict a function's value at some distance h away from x. So what we do is, what Taylor series does is it provides us an approximate value in terms of this polynomial Pn and an error. Now, we don't know the actual error because we don't know where to evaluate this remainder term. This remainder term, we need to evaluate this derivative at zeta. All we know is zeta belongs in this range from x to x plus h. So what we do instead is we find out what is the largest value of this remainder term in this range, largest magnitude, and that becomes our absolute error bound. So let's again formulate the problem. Let's suppose at some x value, we know function, its first derivative, second derivative, so and so. And we also know how many terms or how many derivatives we have. And then our goal is to predict or find or approximate the value of function at x plus h. So the key idea here is we are going to create an approximate value, which is our polynomial value, and we are going to calculate absolute error, but we cannot because we don't know zeta. So all we will do is we will try to find the maximum magnitude that this remainder term can have in the range x to x plus h. And then, of course, since it is absolute error bound, we can use it to determine CDDs or ST. So notice, let's summarize something that we have been doing so far. Let's suppose we want to determine one or more unknowns. If we use an exact method with a perfect machine, then we find the true value. So there is no issue of error, imprecision, approximation, etc. However, when we use an exact method or an iterative method, and we use it with a finite or limited precision machine, like our calculators or computers, what we do is we get an approximation, and we should be always be getting an absolute error bound. We should be always be able to calculate it. So notice in this course throughout, whenever we have made an approximation, we have always been able to bound the error. Now think about, do any of your courses, either theory or lab, teach you to reliably determine both the approximation and the error bound? Think about it. So again, let's take a look at our Taylor series. We said we have fx plus h. This is our approximation. And this is our error bound absolute. So what we do is we always say Rn, if it is less than equal to 0.5 times 10 to the minus CDD, because it is absolute error bound, so it is related to CDD. If we want to relate relative error bound, now our relative error bound would be so it's absolute error divided by true value, but we don't have true value, so we will use approximate value, and this would be our relative error bound. So now we can compare it to 10 to the minus SD, significant digits. So that's the key idea. Okay, so now we are going to progress and look at Taylor series in two variables. So let's see what that means. So let's suppose we are given a function which is of two variables, x and y. So what we want to do is we want to find the value of this function at x plus h and y plus g. So this is like delta x and this is like delta y. So we want to find this value. So what the Taylor series says is this value is going to be the function xy. I'm not going to write the parenthesis, plus h times partial derivative of this function at x plus g times partial derivative of function with respect to y plus higher order terms. So I have got the second order term here on my slide. So this is our second order term, involves second derivative. So notice I'm using a notation. So if I have a subscript, it means I'm taking partial derivative with respect to x. If I have two subscripts, I'm taking second derivative with respect to x. If I have mixed subscripts, again, two of them, so I'm taking second derivative with respect to x and with respect to y. So this is what these terms mean here. Took me a lot of time to type them in. And this is our remainder term. Now, I'm not going to do any examples or exercises. Not that it is very difficult, but we really don't need that for things we need to do later on. So the key idea here is we are going to use Taylor series only up to first order derivative term. That's the key idea. So our next topic, having done Taylor series, is a system of nonlinear equations. So let's suppose we just solved in one equation, one unknown, right? So now we have, so this was a nonlinear equation, of course. And this one unknown was x. Okay. Now let's suppose we want to solve an equation in two unknowns, and let's number them. X1, x2 is equal to 0. So obviously we need two equations. So this is our first function. This is our second function. So now we have two equations and two unknowns. Our unknowns are x1 and x2. So you can see what I can do is I can write x as a vector, and I can express functions as a vector. And I will have a bunch of zeros as a vector. So this is my system of nonlinear equations. So on a compact notation, I can write n equations in n unknowns, because x's could be x1, x2, x3, x4. Functions could be f1, f2, f3, f4. Okay. So first of all, big picture. If we have a nonlinear system, it may have no solution. Just like one equation, one unknown, it may not have had any solution. We have no way of knowing it a priori before we examine this equation. Just by looking at it, we cannot say. It may have a unique solution. Again, without examining, we do not know it beforehand. It may have many solutions. Again, we have no way of knowing it beforehand. So we have to examine it. Just like when we had one equation, one unknown, what we did was we graphed it to figure out where the curve crossed the x-axis. So where can we use a nonlinear system? Very, very simple. Remember, we just talked about Taylor series. And when I talked about Taylor series, I talked about your calculator functions. So behind each of those functions is indirectly or directly some use of Taylor series. So I showed you, for example, square root function. I showed you sine x Taylor series, cosine x Taylor series. In fact, we don't need to develop Taylor series for each of those functions. So from sine, we can get cosine, we can get tangent, and so on and so forth. But let's see where a nonlinear system might be used. So you have in your phone GPS, and your cell phone towers know exactly where you are. So this is done by trilateration. So there are three satellites located at, let's say, x1, y1, z1. These are the coordinates in a coordinate system. Second satellite located at x2, y2, z2. Third one located at x3, y3, z3. And your GPS in the phone knows location of these satellites and the distance your phone is away from each of these satellites. So let's say the distance is R1, R2, R3. So from your coordinate geometry, you know that this distance R1 square would be difference between x minus x1, where x is your x coordinate, y coordinate, z coordinate. So you can write three equations like this in three unknowns. So your coordinates are x, y, z. These are your three unknowns, and we have these three nonlinear equations. So of course, again, we may have no solution. We may have a unique solution. We know probably we have definitely one solution. It may have many solutions too. So we don't know beforehand. But anyway, you can see where a nonlinear system solution might be needed to locate your cell phone location. So let's start by looking at a 2 by 2 system. So ordinarily, if we have a 2 by 2 system, we would begin by writing. We have two equations in two unknowns. Like this. What I want to do is, since it has got too many subscripts, 1, 2, 1, 2, and it is easy to get confusing, what we will do is we'll say x1 is same as x, x2 is same as y, and then f1 is same as f, but f2 we'll name as g. This way we remove all our subscripts. So our two equations and two unknowns become fxy is 0 and gxy is 0. So what do we do in our iterative methods? In iterative methods, we begin with the initial guess for our unknowns, x and y, and then we compute fx and y and gxy. Obviously, we may not have guessed perfectly, so both probably are not 0. So now we need to find corrections, delta x and delta y, so that we can improve x and y. And we will keep on repeating steps 2 and 3 till delta x and delta y become small enough. So that's what we have been doing. So we just need to find a method how to find corrections delta x and delta y. So again, you can guess we are going to use Taylor series. So we use Taylor series and we say, okay, let's find function at x plus delta x and y plus delta y. So it will be f at xy plus delta x times first derivative of f with respect to x, delta y times first derivative of f with respect to y. And we are going to ignore higher order terms. Let's also expand g by Taylor series. So we will have g plus delta x, remember this is like h times the derivative. So function g with respect to x plus delta y times, okay. So I have this on my slides too, and I've said higher order terms we are going to neglect. So what do we want? We really want delta x, delta y such that next time we do the iteration, this function becomes 0, because that's what we want. We want function at those root values, at those solutions, to be 0. So what we are going to do therefore is we are going to bring f and g to left hand side. So we will get minus f is equal to, and now we'll be left with this, right? We'll be left with delta f delta x dx times delta x plus delta f delta y times delta y minus g is partial derivative with respect to x, partial derivative with respect to y. Okay, so you can see now we can write this in a matrix form. So we collect all these derivatives times delta x delta y is minus f minus g, right? Okay, so this matrix is called Jacobian. So we'll write it as J, it is 2 by 2. So this is our delta matrix, which is 2 by 1. And this is our F matrix, which is 2 by 1. So obviously, once we have initial guess, X and Y, we can calculate F and G. So we know this. If we know the partial derivatives at our initial guess, then we know J, so we just need to solve for delta. So let me repeat this. So we got our equation, J times delta is minus F. So if we want to solve for delta, we will get J inverse times F. And once we have got delta, so we can start with an old guess and we can add delta to it. So this is just like X. So this is our initial guess, right? So our equation becomes X new is X minus J inverse times F. Notice this is like partial derivatives, right? So it is like dividing F by its derivatives. Remember when we did one equation, one unknown? Newton's method. What was our equation? X new was X minus function over function prime. So this 1 over F prime is like Jacobian inverse. So very similar, analogous to one equation, one unknown. So when should we stop? We'll stop whenever delta becomes small enough. So let's say we want to use some kind of a criteria. So we could use any of our vector norms. Vector norms are usually absolute criteria. So we could use Euclidean norm, norm 2, and say stop iterating when delta norm becomes less than this. Now in Excel, we can find this by using these functions. So we can do square root of the sum square of the vector, which is our delta vector. Okay, let's do an example. Oh, before that, let's look at convergence of Newton's method. So when we did Newton-Raphson method, one equation, one unknown, we looked at derivatives. Now in this case, since we have lots of functions, what we want is that the partial derivative magnitudes should all add up to less than 1 in the search interval. And then convergence is guaranteed. In practice, we seldom test for convergence. We just go ahead and try it. In most engineering problems, we know if solution exists, it's probably a reasonable values that we can estimate and we can find that solution. Okay, so let's do an example. We have two equations and two unknowns. So our first equation is x squared plus y squared is 4. You know, this is the equation of a circle. Our second equation is 1 minus e to the power x is equal to y. So now what we want to do is we want to write them in the form something is equal to 0, because all our functions f1 equal to 0, f2 equal to 0. So what I'm going to do is I am going to subtract left hand side from right hand side, just arbitrarily. For the second one, I'm going to do the other way around. I'm going to subtract the right hand side from left hand side. Just to show you there are many ways of getting this f is equal to 0 for. So of course, this is our two equations in two unknowns. This is our function f, this is our function g. So our Jacobian is going to be partial derivatives. So here is our equation. I'm going to take partial derivative of this with respect to x, partial derivative of this with respect to y, partial derivative of this with respect to x, partial derivative of this with respect to y. And remember, our function is 4 minus x square minus y square, 1 minus e to the x minus y. Okay, so we have our Jacobian, we have our function. All we need is an initial guess. So let's visualize these two equations. Okay, so of course I used a computer to draw it on my slide here, but it is easy to visualize this. Let's say this is x, this is y. So this is, we know, equation of a circle centered at the origin. So this is plus 2, minus 2, plus 2, minus 2. Like that, right? Okay, now let's plot this equation. So this equation is y is 1 minus e to the x. So if you look at e to the x, e to the x looks like this. So if you want to do minus e to the x, minus e to the x would look like that, right? And then we add 1 to it. So this was 1. So if we add 1 to it, the curve would look something like that, right? So our curve looks something like that. So this is 1 minus e to the x minus y, right? So you can see it has got two solutions. So one solution looks like somewhere around minus 1.7 and something close enough to 1 or so. Other solution looks like 1 and about minus 1.7, something like that. Right. Okay. So what we are going to do is we are going to start with the initial guess of 1 and negative 1. So we are shooting for this solution. Instead of using initial guess 1 and minus 1.7, I'm going to use minus 1 just to make my calculations easy. Okay, so again, I want to repeat here. J is minus 2x minus 2y minus e to the x minus 1. And f is 4 minus x square minus y square 1 minus ex minus y. So we'll start with our guess. 1 and minus 1. So we calculate our Jacobian. So minus 2 plus 1 plus 2, sorry, minus, I'm going to keep only 4 significant digits. That's minus e to the x at x is equal to 1 minus 1. Let's calculate the function. So I'm going to use my calculator. 4 minus 1 square minus minus 1 square. So I'll get 2. 1 minus e to the x minus 1, we will get minus 0.7183. Okay. So we want to solve for delta, and remember, J times delta is equal to F. We are going to forget the negative sign for the time being. So to solve for delta, we are going to use Cramer's rule. So to Kramer's rule, we need to first find determinant of J. So we find determinant of J, this times this, minus this times this. We will get 7.436. Please do these calculations along with me. If you don't, you will not realize the details that I am going through. So if we want to find delta x, what we are going to do, our denominator is 7.436. In the numerator, we are going to replace first column by right hand side. So we are going to do 2 minus 7183. This remains the same. So when we calculate the determinant, divide by this, we'll get minus 0.07572. Remember, I'm keeping just 4 digits by hand. Let's calculate delta y. This time, we are going to replace the second column by the right hand side. So this remains the same. This becomes 2 minus 0.7183. So we solve for it, we'll get 0.9242. So our new x would be therefore old x, which was 1, minus delta x. So we will get 1.076. Remember, rounded 4 significant digits. And our y new would be 1 minus 0.9242 minus 1. We'll get minus 1.924. So this would be our new guess, and we are going to put in here and repeat this whole process. So this is just one iteration. So you can see just even for 2 by 2, it is a lot of work. We know that our solution is going to be somewhere like 1 and negative 1.7. So you can see we are getting there. Of course, the best thing would be to implement it using a spreadsheet. However, what you should do, just for practice, you should do one more iteration on your own using pen, pencil, paper. Okay, please do that. Next thing we are going to learn is how to do it in Excel. Okay, so let's see how we are going to program it in Excel. I'm going to try to keep it very much like how I have done it using paper and pencil. But remember again, our functions, we have Jacobian is minus 2x minus 2y minus e to the x minus 1. And our function is 4 minus x square minus y square 1 minus e to the x minus y. Okay. So in Excel, we would need to therefore define these functions. So we'll do that using VBA. Normally in VBA, whenever we are giving a dimension to a matrix, so suppose we say dimension matrix A and we make it m by n. So what it means is basically that these indices go from 0 through m. 0 through n. So it starts numbering from 0. In matrices, we don't start numbering with 0. We start numbering with 1, first row, first column. So we can change this base. And we do this by using this first line, say option base 1. Now when we say option base 1 and we give a dimension to A and we say m by n, now it means 1 to m and 1 to n. Okay. So here I'm going to start saying option base 1. So here is my function. My function is function of xy, and I am going to make it a variant size, meaning that VBA will figure out from the context what type f is. Is it a single value? Is it a vector or what? Now I know that I want this function to be a 2 by 1 vector. So I'm going to create a matrix. I'm going to say 2 by 1. Now, if I had not done option base 1, one way I could have forced it to start from 1 is to say start dimensioning matrix 1 to 2 and 1 to 1. Notice later on when I'm going to do Jacobian, I could do 1 to 2 and 1 to 2. But since I set my option base at 1, you can see I can write it in a more compact notation. So I could have written here 2 comma 1. So my matrix 1 1 is my first function, second function 1 minus exp minus y, and then I say this f is this 2 by 1 matrix. Same way for Jacobian, I set up a 2 by 2 matrix and I say 1 1 is minus 2x minus 2y minus e to the x minus 1. So you can see these are all basically the functions which are elements of these two matrices. And then I say Jacobian is this matrix, so Jacobian becomes a 2 by 2 matrix in this context. Okay, so let me fire up my Excel spreadsheet. So here is my template. So let me overlay over here. Okay, so just to let you know, I've already typed in my module 1, which are these two functions I just talked about. So we'll start with our guess, 1 and negative 1. Oops, we always start with naming things, right? So we are going to call this matrix Jacobian. So we'll call this matrix just J. Actually, let's make it matrix J. Okay, we'll call this matrix F. Okay, we'll call this matrix J inverse. And we'll call this matrix delta. Okay, so first thing we do always go to formulas, name manager, and we have these 4 names. Okay, so we are going to calculate this matrix using our Jacobian function, which requires 2 arguments, x, comma, y. Remember, control, shift, enter. Okay, this is our f function. Again, requires 2 arguments, x, comma, y. Control, shift, enter. All right, we want to take J inverse. So we are going to write M inverse of matrix J. Control Shift Enter. So now our delta would be matrix multiply of J inverse by matrix F. Control Shift Enter. And of course, our new values would be whatever our guess values minus delta. Oh, did we not name this? Let's name this guess also. We'll name that as old. Should be easier to write. So we'll say this is equal to old minus delta. Control Shift Enter. Great. Now we are going to calculate the Euclidean norm of this. So we are going to say equal to SQRT of sum square of delta. Okay. And let's say we want convergence criteria. This is absolute. So let's say we'll say less than equal to 1e minus 7. Okay. So let's make some, keep some records. So we are going to take this guess, copy. Remember, we want to just paste values. We are going to take this, copy, paste values. Okay. So now this new guess, what we are going to do, we are going to copy it and paste special values only here. So with this with these new values, we go through Jacobi matrix calculation, function matrix calculation, inverse, delta, and we get our next guess. So what we are going to do is we are going to take this value, copy, paste it here, and we got this delta with that initial guess, right? Then again, we are going to copy this, use it as our next guess. Remember, you're always copying values, not formulas. Keep a record here. And also notice that this vector norm delta is decreasing quite rapidly, you can see, by factors of 10 or 100. So now we are going to take this, copy, paste here, and now we are to 10 to the negative 5. Copy, copy this. Oops. All right, next guess. Now when you do this lab, I'm going to have you create a macro so you don't have to do this copy paste. So you can see we just converged. Because our delta became less than 10 to the minus 7. So our final answers are these. That's our final answer. So you can see graphically we had guessed approximately 1 and negative 1.7, and that's what we are getting now. So this is our last slide.